Good day again, everyone. Welcome to another tutorial by M.I.B. Math is Beautiful. Please do remember to subscribe and hit the notification bell. Keep your comments flowing and questions. Today we'll be looking at proof by mathematical induction. Now what we'll be doing, however, in this tutorial is to look at the principles of mathematical induction and the steps taken in answering the question and just an understanding of what it is. Now, if you recall, back in one of the earlier tutorials, we looked at about 4 different proofs. Those were all deductive proofs. Basically, we drew a conclusion based on something known or assumed. Now, mathematical induction, it is not a deductive proof. However, it's an inductive proof by which we prove general statements about positive integers. In other words, inductive arguments make inferential claims, right? That since the premises are true or acceptable, then it follows that the conclusion must indeed be true or acceptable as well. Now, notice that the deductive proofs or arguments had sound premise. That is, they had a sound premise of a proof or theorem or axiom. With the inductive proofs, we are actually looking at or making inferential claims, right? To say that since a premise is proven true, then the conclusion must follows. That is all we are doing with mathematical induction. Now let us look at the steps involved in proof by mathematical induction. Now there are 4 basic steps that I follow, and which are 4 simple steps to follow in proving doing proofs by mathematical induction. Now the first step is to prove true for n equals 1. Right? So whatever the formula is, you ensure to prove it true for n equals 1 by putting n equal 1 wherever n is and to proving true, right? Then the second step is to assume true for a different number. So you're saying that if you have proven true for n equal 1, you want to assume it true that it will be proven true for another number, whatever the number is. So let's just say the number is 43. 34, whatever the number, just a random number. So you're using a different number from n equals 1. So you're proving it true or assuming it true for a different number, and you call that number k, right? Then what you'll do now is that you're required to prove true for n equals k plus 1. Because whatever that number is k, it is different from n equals 1. So, and this number k must be after n equals 1 in the sequence, because n equal 1 is generally the first term. Right? So you are required to prove true for n equals k plus 1, where k plus 1 is a number after k, right? Hence k plus 1, right? Now once you prove step 3, or step 3 has been completed and proven, then it should be concluded that the initial statement is true for all positive integers given. Now let us look at the basis of mathematical induction, right? And my reasoning is that the basis of mathematical induction is like a train of dominoes. Of course, we're going to use some circular dominoes for ease of graphing my explanation here, right? But let's just say we have some dominoes. Right? These are dominoes. And of course, these dominoes represent statements. Right? So this would be n equals 1. Correct? This would be n equals 2, n equals 3. Goes on to where n equals k, whatever that number is, hence the ellipses, right? And then this would indeed be k plus 1. N equals k plus 2 and n equals k plus 3. Correct? Now, if this is the case, following the steps to prove mathematical induction, we are going to use that in reference to the dominoes, right? First, we will prove true for n equals 1. So, we are saying that suppose the first statement is proven true, right? Which is n equals 1. Then, this domino will indeed fall and knock n equals 2. And then, n equals 2 will fall and knock down, and it will actually knock down n equal 3, right? So therefore we are saying that n equals 1 is proven true once we put in n equals 1 into the function that was given. And once that is proven true, it falls and it knocks down the subsequent dominoes, right? Then we moving on to step 2, we are assuming true for a different number k. So we are basically saying that suppose the kth domino falling hits down the k plus 1 domino. So because already we assumed true for k, for n equal k. So basically this is now proven true because this was assumed true. So we're saying that suppose once you prove this true, then this, if this is proven true, then it will actually do the same effect that n equal 1 did, which was to hit down the subsequent dominoes. So if the n equal k is proven true, then this will actually knock down the domino, which is n equals k plus 1. Correct? So therefore, if it knocks down n equals k plus 1, it can be shown that n equals k plus 1 is actually proven true as well. Right? Now if n equals k plus 1 is proven true, then it continues to knock down all the subsequent dominoes in that train. So basically, once n equals k plus 1, or the k plus 1th term, is proven true and everything falls, then it is reasoned that all the dominoes after will also fall. That is, all the statements within this induction is proven true. And this is the general basis of what mathematical induction is. Once you follow the steps, then indeed you will or must end up with a plausible or viable answer from the mathematical induction. Please continue to part 2 of proofs by mathematical induction, where we'll actually look at questions in full. Thanks for watching this video. Please like, subscribe, hit the notification bell, leave your comments, and visit us on Facebook at M.I.B. Math is Beautiful.